I want to do some more rotations of rigid object stuff, and I'm not sure how far I'm going to get in my calculations and making videos, but I do want to do another Monte Carlo calculation of a moment of inertia tensor. I previously did this for a cube, and I want to do it for a cone, and so let's just start talking quickly about the moment of inertia tensor, and then I'll set up the calculation, and then we'll make it in Python. And I actually don't know that it's going to work because I haven't done this yet. So let me turn this camera off. Okay, so here's the deal. I have a cone. It has a mass m, and it has a radius at the top of r. It's centered on the origin. Actually, this is the z-axis. I use this from the book. So that's oriented on the z-axis. I guess I'll do that just the way they did it. So what is the moment of inertia tensor? If I have a rigid object and it's rotating, then the following is true. The angular momentum and the angular velocity are related by this moment of inertia tensor, so they don't have to be in the same direction. And then I can find the components of the moment of inertia tensor. Ixx would just be the sum of the mass. If I had broken into individual masses, the sum of the mass times its y, each mass is y component squared plus its z component squared. And then I'd go through and do that for all the masses. Iyy would be the same thing, but I'd have x squared and z squared, and izz would be x and y squared. Okay. Now, if you don't have discrete masses, you'd turn that into an integral. You'd still have a continuation of individual masses, and that turns into an integral, and it looks like this. Rho dv is the mass of each element piece, and dv is the volume element. And I just put it this way because if I was doing this, I would do it in cylindrical coordinates, so that's why you have that. Now for the off-diagonal elements, this gives you all of those elements. The off-diagonal elements, it's negative the sum of mi xi yi for xy. And you can see that's the same for yx, because if I switch the order here, I get the same thing. And then so zx would be z and x and so forth. And again, that's as an integral. I'm not going to do this integration. Okay, I've already looked up the answer. So the moment of inertia tensor is diagonal if I rotate about this point right here. And so I get r squared plus 4h squared, r squared plus 4h squared, and then 2r squared with this 3/20m constant up front. So I'm going to do this numerically and see if I get the same answer by checking these values. Okay, so how do we do this numerically? How do we do this with Monte Carlo? So the key to a Monte Carlo calculation is to take my cone, and instead of breaking it into an infinite number of pieces, I'm just going to use, let's say, n equals 1,000. Actually, I'll use more than that. And what I want to do is have uniformly distributed masses. I'll make them randomly in here. And then for each one of these masses, I can calculate the moment of inertia tensor, dxixx. That's going to be the moment of inertia tensor due to one of those pieces. It's just going to be mi times yi squared plus zi squared. And then I can just add up all the pieces. Now the question is, how do you generate 1,000 points in a cone? Well, in Python, I'm going to use the random function. So random, just like that, it's going to give a number between 0 to 1. Okay, so it's going to be in between those two numbers. Now, if I want to, let's say, we're going to have to pick some values here. So let's go ahead and say m equals 0.1, r, this value, let's say 0.2. I'm just picking stuff. And then h is this value. Let's say h is 0.3. And this is kilograms, and these are meters. Okay, so then I can do the numerical calculation. So how do I generate a point that is in the cone? Well, I can do this. I could generate a temporary position, and I'm just going to write this as rand, which is short for random. That's my vector. So I have an x, y, z component. But if each one of these is between 0 and 1, 0 and 1, 0 and 1, I would get this. I'd get a box. Like that, where the center is at the it's not even a box in the right location, right? So that's what I would get. So what I need to do is to shift this box over so that I have a box with the origin right here. So let's draw our box. I need to do two things. I need to have the origin right there in the center, and then I need to restrict this to a cone like that. Okay, so there's two things. And I want to make sure I maintain uniform distribution before I cut them. So I'm going to generate these points, and then I'm going to say if it's in the cone, keep it. If it's not, throw it away. Okay, so the first thing is, how do I get this? I want this to go from let's say, negative, this should be, no, this is generate a cone. It doesn't have to be R. I want to do a 1 by 1 by 1 cone. Okay, and then I can cut out the pieces after that. If I do that, I make sure that everything's uniform. So this is my X direction. I want it to go from negative 0.5 to 0.5. So I could say this, 0.5 times 1 minus 2 times random. So random would give me between 0 and 1. So this could be as big as 1 times, oh wait. Yeah. This would give me as big as, this could be as big as 1 or as big as small as negative 1. And then I multiply by 0.5 and I have a total length of 1. So that's what I'm going to do for my X and my Y direction. For my Z direction, I want it to just go to 0 to 1. So I can just say random, 0 to 1. And then I can cut the pieces out. Okay, so that's what I'm going to do. Okay, let's jump over to Python and let's see if we can first make the cylinder and then we can find the moment of inertia tensor. So let me switch over to the computer. Okay, so let me go ahead and put in my values here. First thing, I had R equals 0.2, M, big M, equals 0.1, H equals 0.3. Now I need to say how many pieces I'm going to break this into. Let's say N equals 100 at first, and N equals 0. And again, this is not the best way to do this, okay? Because there's better ways to count. But I like to do it this way because it makes sense to people. They can understand it. Now, the next thing I need to do is find the mass of each individual piece. So let's say dm equals m divided by n, right? Because if I break this into 100 pieces, then each little piece will have a mass of 1/100th times the normal mass. Okay. Now, there's another thing. If I go back to this cone, let's just generate the points first. Okay. So I'm going to say while n is less than n, and I'm going to make a temporary vector. R temp equals vector. Then I said in the x and y direction it'd be 0.5 times 1 minus 2 times random. And then I get my parentheses mixed up. That's also the same for the y direction. So I'm just going to copy this because I mess up with my parentheses if I don't. And then my z direction is just going to be random. And that will, so all of these will be have a length of 1, right? They'll go from 0.5, negative 0.5 to 0.5, or 0 to 1. And that's important so that each, the distribution is in the same scale, right? If I had my z go from 0 to 0.3, then all those numbers would be squished down in there and there wouldn't be a uniform distribution. So let's just plot these. So I'll say sphere position equals r temp. Radius equals, let's say r divided by 20. I'm just making up something. Now I need to add 1 to n. N equals n plus 1. And let's run that. There you go. So that's 100 data points. And it does look like it's centered at the origin. Let's just do 1,000 because it'll look more like a cube. Yeah, I think that's right. Let's do this. Let's just double check. Let's just print r temp. and see what we get. I'm just double checking here. Okay, so I want my x and my y's between negative 0.5 and 0.5, and my z between 0 and 1. So just double checking. Yeah. Okay, I think it's good. Okay. Now, how, and I didn't want to print 100 of those, so let's go back to 1,000. Okay, so now how do I make sure this is in a cone? Well, I want to do two things. First, I want to make sure that the z value is not greater than h. Okay, so I'm going to go down here. I'm going to generate my 1,000 data points. And then I'm going to say if rtemp.z is less than h, then make a sphere and increase n. And so all that's going to do is cut off all these numbers that are greater than 0.3. Let's run that. It's hard to tell that that's, oh, that's right, because see, so now I have a skinny box. The z axis is out of the screen. So there, I cut it off. It's a lot skinnier. You see that? It's still 1,000. It should still be 1,000 data points because I only increase in if it was smaller than that. Now, how do I cut off the other one? I want to cut off the other one. Let's switch over here to the paper so I can draw this. Okay, so here's my cone. Let's say that this is the z axis and this is the r axis. Okay, and so r is going to be equal to the square root of x squared plus y squared. And then this is my cone angle. So the slope of this, m, is going to be equal to h over r. Is that right? Yeah, because if I rise or run, so it goes up h and over r. So this is like the line z equals mr. And I want to be less, I want to have mr, I want to have r less than, so I want to say r is less than z over m. Okay, if r is less than z, because as I go up higher and higher, then I can go further and further over. But as z gets down to 0, I don't want to have any of those points. So I need to check this. So I want to have two things. I want to have z less than h and r less than that. So I can go back over here to the computer. Let's wait. There we go. And I will say if z is less than h and the square root of rtemp.x squared plus rtemp.y squared is less than rtemp.z divided by m. And m is the slope of that, which is, I said it was h over r. Is that right? I think that's right. Yeah, I think that's right. Okay, let's run this and see what happens. And it looks like a circle. And it looks like a cone. That looks like a very, let's see, r is 0.2. Okay, let's change this to r to 0.1. I want a little bit skinnier cone. Looks more like a cone. Okay, I'm pretty happy with that. So let's say r is 0.1. So this distance is 0.1, and this distance is 0.3. I mean, I guess so. It's kind of hard to tell. It looks a little flat, but let's increase the number of data points. That looks cool. Why is it all curved down there? I think I made a mistake. Because I don't have a point. Let's see, so and square root of rx squared plus ry squared is less than or equal to rtemp divided by m. If rtemp.z is less than h, and, see, there's no point. What happened to the point? Why is there no point? Sphere, rtemp. Let's see. 1 minus 2 times random. 1 minus 2 times random. Oh. No, in random, that's right. It just doesn't look right. I mean, it looks cool, but it doesn't have a point. And if rtemp.z is less than h, okay, that cut that off. And the square root of rtemp.x squared plus rtemp.y squared is less than rtemp.z divided by m. Oh. 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 I took the square root of the whole thing. Wait. Oh, that right there. Right here. That's better. Okay, so let's put this r back to 0.2. It didn't look right, you know. And let's make the ball a little bit smaller. Let's see, so I have this, it's divided by 40. There we go. There's my cone. Check that out. Okay, so now let's calculate IXX. So I've plotted my points. I don't even have to plot them anymore. I don't really have to do that. But I'm going to do, I'm going to leave that on for right now. So let's do, let's say this. IXX, oops. IXX equals 0. So this is my counter, right? I'm going to find the moment of inertia to each sphere and add it to this thing. So, but I'm only going to do it if I'm making a sphere. So over here, I'm just going to say IXX equals IXX plus dm times its x component squared. So that's going to be r temp dot, I'm sorry, y component squared plus its z component squared, r temp dot z squared. Let's go ahead and calculate, what was the one that was off? Let's see, the z component. Let's do z and let's do xy. So izz equals 0, and then ixy equals 0. Let's calculate all this. Okay, so izz, it's just going to be the same thing. Izz plus dm times r temp dot x squared plus r temp dot y squared. And then finally, ixy is going to be xy equals ixy minus dm times r temp dot x plus times r temp dot y. Okay, so then let's run that and print these things out. So let's say print IXX, IXX equals, I'll leave off the units because I'm lazy, IXX, print IZZ equals IZZ, print IXY, IXY. And now I need to calculate the theoretical values too. So let's say IXX theory is equal to, now I'm going over my equation, it's 3, let's see, put it 3 divided by, times m, divided by 20, times r squared, r squared plus 4h squared. Plus, not equals. Okay, that's the theoretical. Let's do the same thing for IZZ. Theoretical is going to be equal to 3 times m divided by 20 times 2 times r squared. IXY in theory is 0. So let's print IXXT equals IXXT. Print IZZT equals IZZT. And let's just leave off the other one because 0. Okay, let's run this thing, see if it works. And I have a mismatch in parentheses. Big surprise there. Okay, so here I get Ixx is 5 times 10 to the negative third. Here I have 6 times 10. That's win. I just won right there. Okay. Izz is 1 times 10 to the negative third. 1 point. That's pretty close too. And then for Ixy, it's 3 times 10 to the negative 6, so 1,000 times less. So that's pretty close to 0. We can do this. Watch this. If I turn off the sphere thing and then increase the number here, it will run a lot faster. I think. I could be wrong. I did it. Okay. So again, I'm getting, that's still pretty large. Ixy I thought it was supposed to be 0. Well, it's still pretty small. It's still pretty small. And those are the ones that agree very well. Okay, now let's move this down. And you think, well, you know, this is kind of stupid because I could have just done this on paper and, you know, what's the point? And I'm going to show you the point. Okay. So this is the calculation of the moment of inertia about that point right there. Oh, you know what? I covered up my, are you covering up my answers with my video? I can't see. Hold on. No, I think you can see it. I'll leave it on. I know you want to see me. You'd like to see my facial expressions. Okay, so that's about this point right there. But what if I move the point about which I calculate the moment of inertia tensor? And I should save this. Cone inertia tensor. What if I have some point, some rando point? What if that point's like way over here? I mean, then how would I calculate the moment of inertia tensor? It would be tough. There are ways to do it, but it would be tough. But with a numerical calculation, it's not so bad. Let's just say point O equals sphere. Position equals vector. Where should I put my point? Let's say in the x. Let's put it in the xy plane. So let's say r 0. And let's give it a radius of r divided by 10. I don't know. And let's give it a color yellow. Okay, let's just run that and see what it looks like. Okay, so there's my point. That's a little big, but that's fine. It's not a real point. It's just an imaginary point. Now, I want to calculate the moment of inertia tensor, so I'm going to do the same thing. I'm still going to generate the same points, but when I get down here, I need to find the new r value. So think of this. What is the location of each point with respect to that new point? So if I just take that point minus the observation location, that's my new r. So I can say this. Let's do this. R equals, 0.0, that's weird. Let's call it observation. OBS. Yeah, that's fine. So R is going to be the actual point, which is R temp, minus obs.pos. obs.pos is the position of that point. Now down here, I just need to switch all these just to R's. Because that's my new, I didn't use R before, did I? I want to make sure I'm not double using R. There's that. Something flying over. Something very loud. I want to see what it is. I don't see it. Okay. Okay, that should work. Let's just do it. Okay, so now you see here my moment of inertia tensor. Ixx is 9.9 times 10 to the third, which is different than the theoretical value, right? Because now it's further away. It's going to be different. And so it's harder to check these things, but it is different. So that's what makes this calculation so much more powerful, right? I can just put my point anywhere and I can calculate the moment of inertia tensor. Now, I should point down here that Ixy is no longer 0, okay? Because we don't have that same symmetry to balance on. Okay. I think I'll stop there. The difficulty here is constructing these points so that they are in your space that you want. I want them in a cone. That was, I think, the only difficult part. Everything else other than that was just, plugging it into the moment of inertia component equation. So, okay. I will give you this code down below. I'll link down below the video on the cube Monte Carlo calculation, and hopefully you enjoyed this. But if you didn't, I don't know what to say. Maybe you have a good day anyway. And I will talk to you guys later. Where I find my stop button, there it is.